Proof by induction. This is a divisibility example for Leaving Cert High Level Maths, also called a factors example. So we're asked to prove that this expression is divisible by 7 for all values of n. We're going to use induction. Step 1, we're going to use the lowest value of n equals 1. When we sub 1 in for n into the expression and evaluate it, we see that the value of the expression is 7. And 7 ones are 7, so 7 is clearly divisible by 7. So we can say it works for n is equal to 1. Step 2 is we're going to assume it to be true for n is equal to k. So we write down that we assume when we sub k in instead of n into this expression that it's divisible by 7. Divisible by 7 means it would be equal to 7 groups of some number, where that number would be an integer. So we'll call that number a. Now we're going to now, having made that assumption, try prove that it is true for n is equal to k plus 1. So I sub k plus 1 instead of n in the expression. Now I'm going to manipulate this. Looking at the first term, the important idea here is that a to the power of k plus 1 is 8 groups of a to the power of k, using the laws of indices. We have 8 groups of 8 to the power of k. That would be the same as 7 groups of it plus 1 more group. The reason for doing this is I want to show that everything is divisible by 7. So I'm taking 7 groups plus 1 group. And what I'm left with then is 8 to the power of a k minus 7k minus 7 plus 6. Now I'm going to use the assumption we made. Let's compare this expression with the assumption that we have. So we see the assumption has this 8 to the power of k term, a minus 7k term, and a 6th term. So using this, I can rewrite my expression, exchanging what I've highlighted in blue for 7a. Now you notice each of the 3 terms here are all divisible by 7. I take out 7 as the highest common factor. I've proven what I've been asked to prove, that 7 is a factor. The final step in the 4-part steps of induction is I state my conclusion. So we have shown that it is true for n is equal to k plus 1, given that it is true, or if it is true for n is equal to k. We've shown that it's true for n is equal to 1. And therefore, it must be true for all values of n where n is a natural number.